Hi, Math 316 students. In this video, we're going to talk about the last part of Chapter 7, the part following cosets and Lagrange's theorem. We'll see some consequences of those ideas. And I want to start this video just by pointing out something. It's not listed in your text, but it's something we've mentioned several times during the course. Here's a Cayley table for a group. I believe this is one of the groups in the wiki. If you were to look at that very closely, you would notice that this Cayley table, like many we've seen so far, has a block structure. And we've talked a little bit about why these blocks happen. We haven't said much, but we've started to notice some things. In particular, what we noticed is that when you have a block, then that block that contains the identity, in this table that would be alpha, that block is closed under the operation of the group, right? And so we know what that means now. If you have a finite subset that is closed under the operation of the group, then that subset is a subgroup. Well, what I want to talk about today are cosets of that subgroup. If we were to take a look at the Cayley table and we were to take an element like epsilon, and if I wanted to find the coset of this subgroup, alpha, beta, gamma, delta, say I were to call that set H. The coset epsilon H would contain the elements epsilon times alpha, epsilon times beta, epsilon times gamma, and epsilon times delta, and that's exactly what we see listed here in these first four columns in the epsilon row. Now, these are the elements of the coset epsilon H. Now, if I were to take, though, zeta times H, I'm going to get these same elements there, and eta times H gives me the same elements, and theta times H gives me those same elements because I'm seeing that this block is there. And now we can kind of understand why. The reason why you'll get these same elements is because these are the elements that I saw in that epsilon row. These are the elements of that coset, and we know that if you have a subgroup H and you form a coset using something from another coset, the coset you'll get back is the same coset as the first one. All right, so this doesn't completely explain the whole block structure. This maybe tells us why the blocks happen in this order. It's because when I chose to list the elements of this table, I did it knowing what the cosets of this subgroup were going to be. Now that will give you the blocks in the first column, but that won't necessarily explain why you see the same blocks to the right in the table. The reason that happens will be because of something special about this subgroup, which we'll mention in a couple chapters. In a couple chapters, we'll talk about normal subgroups and explain how that gives us the block structure that we're talking about. But for the meantime, think about that. Think about how cosets of a subgroup might show up in the Cayley tables that we work with. All right, now to get back to what we were talking about before spring break happened, you'll remember that one day I pulled up an article from MathWorld, which is an online encyclopedia of math that Wolfram.com puts on. And in the article for the finite group, you can look here at the webpage mathworld.wolfram.com/finite-group.html. That was an article that contained a lot of information about finite groups, and towards the bottom of the screen, bottom of the article, there was this table, and in this table we have sort of a catalog of the finite groups, all finite groups of order up through order 31. On the left you have here the size of the group, the order, and then you have a collection, a list of all the abelian and non-abelian groups with that particular order, and sort of the count of how many there are of each particular order. Now, as you take a look at this table, you'll start to notice some patterns. You'll notice that sometimes we only have one particular group total for a certain order. For instance, there's only one group of order 1, there's only one group of order 2 and 3, and if we focus on those rows, you'll notice something very interesting about their orders. 2, 3, 5, 7, 11, and 13, these are precisely the prime numbers between 2 and 13. Now, 1's not a prime number, and 15 also is not a prime number, so it's not a perfect pattern, But it does look like whenever you look at a prime number, there's only one group with that order. Now that group is the cyclic group. Wolfram uses C to indicate the cyclic groups. We've been talking about Z. But regardless, we always have a cyclic group of any particular order we want. That's always an option, and you'll see that the cyclic group appears in every row here. But what it looks like is happening is that when your order of your group is prime, that's the only group possible. That's the only group you can have with a prime order. Now, is that true? Is this really a thing? We haven't talked about that yet, but maybe it is. All right, another pattern you'll notice is that certain rows of the table only have two groups of that order. There's one group that is abelian, it's the cyclic group, and then there's exactly one non-abelian group, which turns out to be the dihedral group. Now that happens often enough in the table to pay attention to it. And if you take a look at which rows it happens in, you'll see 6 and 10 and 14 and 22 and 28, which may not look like much until you divide by 2. 6 is 2 times 3, 10 is 2 times 5, 2 times 7, 2 times 11, 2 times 13, and it seems apparent that these are 2 times the prime numbers. It doesn't hold true for 2 times 2. We don't get the dihedral group. There is no dihedral group with order 4. But 2 times an odd prime seems to always give you this same situation, where you've got only one abelian group and only one non-abelian group, and they are the cyclic group and the dihedral group respectively. Now, is that just a coincidence, just a fluke, because we're looking here at the at only certain rows of the table, and if we were to keep looking further down, we'd eventually find a counterexample to that? Or is that always the case? We'll have to talk about it. I'll put the conjectures up here, though. It looks like they're true. It looks like it's true that if G is a group with a prime order, then G is isomorphic to the cyclic group. And if G is a group with order that is 2 times a prime, where P is a prime greater than 2, then G is going to be isomorphic either to the cyclic group, if it's abelian, or to the dihedral group, if it's non-abelian. We'll come back and we'll talk about these two conjectures a little bit later. And as you'll see, Lagrange's theorem turns out to be key in answering these questions. All right, so I asked you to watch another video introducing Lagrange's theorem and cosets last time. To just quickly review, Lagrange's theorem is the statement that if G is a finite group and H is a subgroup of G, then the order of H goes into the order of G. It divides it. It's a factor of it. And the reason why, and another thing we can conclude, is that the number of distinct left cosets of H is the order of G divided by the order of H. So how the proof went was this. We defined what a left coset was, and then we observed that every element of G belongs to at least one of these cosets of H, and in fact no element of G belongs to more than one of the cosets of H. The distinct cosets didn't have any overlap, and therefore they partition the elements of G. That should say G there. Every element of G belongs to exactly one of these cosets. And that meant that we hit everything in the group. And since all of the cosets had exactly the same size, then that means that the order of G has to be a multiple of the order of H. And that's the statement here, that the order of H divides the order of G. And what's more, if you count the cosets that you end up getting, we have whatever we get when we divide the order of G by the order of H. All right, that's the proof. It's actually not that complicated a proof at all once you know what a coset is. So that's kind of the key idea that went into making this proof possible. Today we're going to talk about consequences of this theorem, consequences of Lagrange's theorem. And our first one in the text is just a restatement of something we've already said before. If G is a finite group and H has a subgroup of G, then the index of H in G equals, and we'll fill in the blank there. But first we should say what we mean by this. The notation absolute values of symbols around G colon H, that means the index of H and G, and what that means is the number of cosets of H there are making up G. Okay, so G colon H means the number of cosets of H in G. Now we will be talking about left cosets. You could talk about right cosets if you want, but it's just more convenient just to always think about left cosets. There's no real difference in anything if you talk about right cosets. All right, so with that in mind, how many cosets are there of H in G? Well, we just said that a minute ago. That is equal to the order of G divided by the order of H. All right? Now, another quick consequence of Lagrange's theorem is this statement. If G is any finite group and A is any element of G, then the order of A has to go into the order of G. It has to divide it. Now, why should this be true? Well, we're going to use Lagrange's theorem, which says that the order of a subgroup has to divide the order of the group. And so maybe that suggests what we should do here. Remember that the subgroup generated by A is a subgroup of G, and so by Lagrange's theorem, this number, the order of that subgroup, will go into the order of G. However, the order of this group is exactly the same as the order of A, and so the order of A has to go into the order of G as well. All right, another consequence of this fact is that if G is a finite group and A is any element of that group G, then taking A and raising it to the exponent, order of G, will always get you the identity. Now remember what this means. This means that if we take A and we put it together with itself using the group operation, and we have as many A's as there are elements in G, then we'll always get the identity once we're done simplifying that group operation. Right, now here's why. If you were to think about the smallest number of A's you'd need to make the identity, that's the order of A. Remember, this is how we defined the order of an element. It's the fewest number of times you take that element, you put it together with itself, and you get the identity back. So, since we just got saying that that number divides the order of G would be a multiple of the order of A. And so taking A and putting the order of G as an exponent means you're going to be putting a whole bunch of A's together, and I can take those A's and group them into collections of size order of A, and each one of these will give me a copy of the identity, so I'll just be multiplying a whole bunch of identities together, and that will produce the identity overall, which is what this result said. Okay, now this result is actually useful in number theory. So if you go ahead and take Math 382 from URI, number theory, you'll probably run into these theorems, which talk about modular arithmetic. Let's suppose that A and N are relatively prime positive numbers. If I were to take A and raise it to phi of n and take that modulo n, I would end up with 1. Now phi of n is defined earlier in the text, back in chapter 4. This actually stands for the number of positive numbers that are less than n that are relatively prime to n. And that turns out to be useful to us in abstract algebra because that is the order of the group U of n. Remember, the group U of n was precisely those numbers that are less than n, positive numbers that are less than n that are relatively prime to it. And that's why the proof is true, why the theorem is true. What we can think of is that A is either in U of n or it's congruent modulo n to an element of U of n. And so what we're doing in this expression is we're just basically taking A raised to the order of the group when our operation is multiplication modulo n. And so what we should get back, according to the last statement here, is the identity. And the identity in this group is 1. And so Euler's theorem is really just almost just a restatement of that theorem from abstract algebra, this consequence of Lagrange's theorem. Now, Euler's theorem is the main idea behind what's famously known as Fermat's little theorem. Fermat's little theorem says that for every integer a and for every prime p, a raised to the p modulo p will be equal to whatever a mod p is as well. So it's got a nice, pleasing look there, and it follows almost immediately from Euler's theorem. What we notice is that the number of things that are less than that prime p that are relatively prime to it are p minus 1. All the numbers 1 through p minus 1 are relatively prime to p. And so the previous statement would tell us that a raised to p minus 1 would be congruent to 1 modulo p. If I took that a raised to the p minus 1 and I just times both sides of this congruence by a, I'd end up with this expression there. Now, there's a little bit of detail I'm kind of glossing over. We're not assuming that a is relatively prime well, it is possible that a could be a multiple of p, and therefore this previous result wouldn't exactly apply. But if you check that case directly, along with the argument we just laid out, then you'll have a proof of Fermat's little theorem. So we have some useful results in number theory that have simple proofs coming from abstract algebra, and specifically from Lagrange's theorem, which is nice. All right, here's another consequence. Let's take a look at those groups with order p, where p is a prime. Now you remember from our table from Math World, whenever we had an order that was a prime number, it looked like there was only one group. And so that's what we're going to prove now, that this group has to be the cyclic group. That has to happen if your group has a prime number as its order. All right, we're not going to write out the complete proof, but we'll supply the idea, and you can read about it in your text. So we're going to suppose that G is a group of prime order P, and that's all we'll suppose in the beginning. Now, because G has a prime order, that means it's greater than 1, so there's going to be some identity in there in G that's not the identity. So let's just pick something in G that is not the identity, and then let's take a look at the subgroup generated by A. Now that will be a subgroup of G. Lagrange's theorem says that the order of the subgroup has to divide the order of G, but the order of G was prime, was P. Now, there aren't that many things that go into a prime evenly. There's either 1 or the prime itself, so the order of this subgroup generated by A is either 1 or it's P. Now it's not 1 though, because A was not the identity, and so the order of this subgroup generated by A has to be P, but there are only P things in the group, so then that means that G must be generated by A. This subgroup generated by A is exactly all of G. And the only way that can happen is if G is cyclic. So Lagrange's theorem allows us to prove this result fairly quickly. Now here's the other conjecture we had from the examination of the table in the beginning of the video. We conjectured that if G was a group of order 2 times a prime, where P is a prime greater than 2, then G was either cyclic or dihedral. Now the proof of this is a little bit more involved. We won't go into the details, and the outline we give here won't be completely comprehensible. Don't worry about if you're not able to get it here in the video, but I do encourage you to take a look at the proof in the text. This turns out to be a true statement, and we prove it by looking at cases. First, we take a look at whether or not G has an element of order 2p. Now, if G does have an element of order 2p, then that means that it's cyclic, right? That means the entire group would be generated by that element, and it would have to be a cyclic group. Okay, so that was an easy case. Our next case would be that there are no elements of order 2p. Now remember, by our consequence, every element of a group divides the order of the group. If the order of the group is 2 times a prime number, the only possible numbers that go into that are 1, 2, the prime p, and 2p. Now we just got rid of the case where there was an element of order 2p, so then every element has to have either order 1 or order 2 or order p. Now only the identity has order 1, so every other element has to have order 2 or order p. So the proof starts by showing that G has an element of order P. They're not all of order 2. There actually is something that has order P. We're going to take a look at that subgroup generated by A, and then we're going to choose something B that is not in that group. Now, there's a little bit of a technical lemma you need to make this work, but it's possible to show that that element B that's not in the subgroup generated by A has order 2. Now, what that means then is that your group consists of the identity, these elements of order P that are generated by A, and then everything else has order 2, which maybe starts to sound a little familiar. These are kind of like the rotations and the reflections of the dihedral group, but we haven't proved yet that that's the case. What we do is we show that because of these properties, the order of B is equal to 2, and because of our technical lemma, every you do have this this statement. This statement has to be true for all A's and all B's in the group. Let me say that again. This element A and this element B satisfy this relationship. A times B in this order gives you the same thing as B times A inverse. Now, what's interesting about this equation is that this allows you to completely fill out the multiplication table, the Cayley table for G. It turns out that every element in G can be written as some power of A put together with either B or no copy of B. And if you ever find yourself multiplying things in this particular order, you can switch the order as long as you change the exponent on the A in this way. And because of that, we can completely fill out the Cayley table. The details are there in the proof if you're interested. But because this tells us everything about how to fill out the Cayley table, wouldn't that mean then that all the Cayley tables of elements of all the Cayley tables of groups that were not the cyclic group looked the same? And it does mean that. What that means is that all non-cyclic groups of order 2p are isomorphic to each other. Every two non-cyclic groups of order 2p are isomorphic. However, wait, we know of one example. The dihedral group has order 2p. It's non-cyclic and has order 2p. And so what our argument shows us is that everything that's not the cyclic group has to be the dihedral group. And therefore, there are only two groups of order 2p. So that's kind of a nice, fun consequence of Lagrange's theorem, and maybe a little bit of technical lemmas as well. Well, having finished that proof, we can go back and we can take a look at this table and feel proud of ourselves. We can completely explain what's going on and why in the rows that are shaded there. Now, these aren't the only patterns you might see as you look at the table, though. And so for the rest of the semester, we're going to start trying to prove other patterns we observe in this table. One thing that we wonder about is this row here, row 15. This is a row that's weird because there's only one group with this order, but we can't explain that by 15 being a prime number because 15 is not a prime number. So why is it that it's not prime, but like the prime orders, there's only one group, the cyclic group, with that order? We should probably figure that out before the semester ends. And then another pattern to take a look at are these rows that are highlighted. These are also rows where there are only two groups available. Now, we talked about the rows in blue here. 2 times a prime number as our order would imply that we have a cyclic group and we have one non-abelian group, the dihedral group. Now, as you look here at groups of order 4, it turns out there are 2 abelian groups. One is the cyclic group and one is this weird C2 cross C2. We haven't talked about what that means exactly. And if I come down here to row 9, we'll have 2 abelian groups, C9 and then this weird C3 cross C3, which is interesting. We'll have to talk about what the cross notation means. Coming down a little bit farther, we find another row with just 2 groups, the cyclic group and then a non-abelian group, but this time the non-abelian group is not a dihedral group, it is some weird F group. Now the article talks about what the F means, so if you're interested, go ahead and read the article, and I believe this is some kind of semi-direct product. We'll talk about direct products. We won't touch semi-direct products, but we're close. We could if we wanted to, if we had more time in the semester. And then taking a look here at 25, we also have two abelian groups, either the cyclic group of order 25 or C5 cross C5. Now, if I sort of lay aside the 21 for a second, 4, 9, and 25 all have this property where we have two abelian groups, and there's a distinct order there. And you'll notice the pattern there, C2 cross C2, C3 cross C3, C5 cross C5. It looks like these rows happen whenever we have the square of a prime number. So 4 is 2 squared, 9 is 3 squared, 25 is 5 squared. So we wonder, is it true that if your group has order p squared, where p is a prime, then you only have the cyclic group or this cross product group as well? If that's something else we should try to look at a little bit later in the course. And that's also just the start. We've only looked at rows that have just a couple groups, but maybe there's something you can say about the patterns that show up. Some of these rows have a lot more examples of groups than others. Is there a pattern to which rows contain which groups? Can you start to explain away all of the possibilities of groups that show up here if you had enough theorems? Well, that's a question we'll take a look at. We'll answer some of those questions here in the semester, and then other questions like that can be answered as you continue studying abstract algebra. All right, so please leave some comments in the questions if you have any, and I will talk to you later.